Hello to all of you. This is Dr. Dhaval Maheta, and today we are going to talk about ARIMA models, basically known as auto-regressive integrated moving average models. The ARIMA models were proposed by Box-Jenkins in 1976. Here, AR stands for auto-regressive, I stands for integrated, MA stands for moving average. Let's try to understand what is the AR terms in ARIMA models. AR in the model assumes that the series is a function of its own past value. That is, the present value of yt is derived by its own past values. I in ARIMA is called the integrated feature. It means that how many times a series has to be different to make it stationary. So, in short, is a transformation done on series to make it stationary. MA in ARIMA represents the moving average in the time series model. MA assumes that in the model, the time series is function of its own error. ARIMA is also known as a Box-Jenkins methodology. Now let us try to understand this AR and MA on the word file. My present value, that is yt, is dependent on yt minus 1 and yt minus 2, that is the previous two legs. So I get this value from yt minus 1 and yt minus 2, and these are AR terms. Now, it may be possible that there may be some error which may be left out. So mu2 minus 1 and mu2 minus 2, they are the terms related to MA, moving average. So mu2 minus 1, mu2 minus 2, MA2 terms, YT minus 1 and YT minus 2 are AR2 terms. Okay. Now, to carry out the analysis, it is necessary that the series must be stationary. It means that the series should have a constant mean, constant variance, and the covariance between different observations should not depend on time, and it depends only on the distance or lag between them. Auto-regressive time series model, if I talk about pure AR1 process, if I talk about pure AR1 process, so yt is only dependent on one past value, that is yt minus 1. So yt is equal to 5, yt minus 1. In my previous videos, we have already discussed about this phi function. For simplicity, we do not include a constant in the model, and we know that the absolute phi value should be less than 1, then only we can create the model. And u1 is a white noise error term. The implication behind the AR model is that the time series behavior of yt is largely determined by its own value, that is its own past value. So whatever which happens in t is largely dependent on what happened in t minus 1 and t minus 2. For example, today's stock prices may be affected by yesterday or day before yesterday. Today's weather may be affected by yesterday's weather or day before. Now, if I talk about generalized ARP, that was AR1. So generalized ARP model is yt is equal to phi 1 yt minus 2 yt minus 1 plus phi 2 yt minus 2 plus ut. And the generalized is t minus p plus ut. So whatever, so this is basically an error term, ut. Please remember this is ut. Now, if we consider this ut also in our model, so we get MA, that is a moving average model. So my yt is also depend upon the errors, the past errors. So yt is equal to ut plus theta ut minus 1. The implication behind the MA model is that yt depends on the value of the immediate past error, which is known at time t. Say, for example, which I had already explained to you, yt depends on yt minus 1 as well as yt minus 2, but it also depends on the errors which were left out in capturing the, or rather, it was a difference between the observed value and the predicted value. Now, the entire ARMA model is represented by phi yt minus 1 plus phi 2 yt minus 2 plus phi p, that's the last term of the AR model, plus theta 1 ut minus 1 plus theta 2 ut minus 2. These are the terms which are related to MA, and last, the overall error. Integrated processes and ARIMA models, we very well have understood that how many terms ARMA has got. But the basic thing in this model is that the series should be stationary. So here I stands for integrated. So how many times we have to difference the series? So how many times we have to difference the series to make the series stationary is denoted by I. If we differentiate the series one time, the I is 1. If we differentiate two times, then I is 2. So most economic and financial time series show trends over time, and so the mean of YT during 1 year will be different from its mean in another year, and therefore it is necessary to make it stationary. So if I say delta YT is equal to YT minus 1, this is the integrated order of 1. If I take the difference two times, then it is I2. Now how the notation of ARIMA is written? So ARIMA into bracket P, D, Q. P stands for how many ER terms are there. D stands for I, how many times the series has been integrated. MA stands for how many moving average terms have been included in the model. A fundamental idea in the Box-Jenkins approach is the principle of parsimony. It means that uh, parsimonious models produce better forecasts than over-parameterized model. It means that if you go on including more and more variables in the model, definitely it is a over parameterized model, and our degree of freedom will, there will be a huge reduction in the degree of freedom, and because of which there can be a possibility of the multicollinearity, and there can be a possibility of spurious regression. The Box Jenkins approach: first calculate the autocorrelation function and the partial autocorrelation of the raw data. Check the series is stationary or not. If the series is not stationary, either take the logarithm or the first difference and try to make the series stationary. Again, examine the graphs of ACN and PACF. And if the series has become stationary, then we approach for the next part. The stages of Box-Jenkins methodology are identification, estimation, diagnostic checking, and forecasting. It is a very well-known fact that lower order MA model is equivalent to higher order MA model. Similarly, a lower order AR model is equivalent to higher order MA model. So instead of using many terms of AR, you can use lower order MA model, and instead of using many terms of higher order MA, you can use lower order AR model. The identification is the identification of the ARIMA is a crucial task for any researcher, and therefore it is known as, it is more of an art rather than science, because on the basis of correlogram, the researcher will have to detect that which AR process the series is following, or which MA process the series is following. So correlogram is plotted based on ACF and PACF. So autocorrelation functions refer to the degree of the correlation of the same variables between two successive time intervals. So here I am only talking about YT and YT minus 1 correlation. But when we compute partial autocorrelation function, we are calculating the correlation between the YT and YT minus 2 and removing the effect, all other effects from between. Say for example, I will remove YT minus 1. So it measures the marginal impact. Let us try to understand this thing on the word file. I want to make a model of YT, YT minus 1, YT minus 2. Now if I calculate the correlation like this, it is a autocorrelation function. But when I calculate the correlation for YT to YT minus 2, removing the effect of YT minus 1, it is known as a partial autocorrelation function. So first of all, check the stationarity with the help of autocorrelation function and partial or autocorrelation function in EViews. And if it is necessary, then transform the series with the help of logarithm or the first difference. After achieving the stationarity, we will have to detect that which process it is. Once we have achieved stationarity, the next step is to identify the P and Q orders of the ARIMA model. So for a pure MAQ process, the ACF will tend to show estimated or autocorrelations, which are significantly from 0 up to the lag Q, and then it will die out immediately after the Qth lag. The PACF for MAQ will tend to die down quickly, either by an exponential decay or by damped sine wave. Don't worry, this is a technical definition. I'll show you how it is represented. So first, let us see the technical definition, and then I'll try to represent the same thing with the help of some graphs. After achieving stationarity in case of AR process, contrary to the MA process, the pure AR process will have an ACF which will tend to die down quickly, either by an exponential decay or by damped sine wave, while the PACF will tend to show spikes for legs up top, and then it will die down immediately. In case of mixed process, both of them will be following a geometry. Now, I will draw the things here only so that you can understand. Say, for example, if I am having ACF function, and this is my correlogram. Just imagine that this is my correlogram of ACF. This is my correlogram of PACF. If I am having, and this is the center line, this is also the center line. If my process is AR1, then I will have a very significant spike at time interval 1, and then there will not be any significant spikes. Moreover, the MA process, in MA process, there will be spikes which are having some geometry like this. So it is a AR1. Here only one spike will be there. If I talk about MA process, it will be completely reverse of this. There will be one spike here, and all other will be insignificant. And the PACF in case will have some geometry. Either the geometry will be exponential or damped sine wave. It can also be that your spikes are following this fashion. 1, 2, 3, 4, 5. It may be possible. Now, if I talk about ARP process, then we will be having a significant lags till P. For example, we will have spikes at 1, 2, 3. This will remain as it is. For MAP process, here we will be having a significant lags till P lag, either 3 or 4. And again, this will be following the geometry. Now comes the last part. If both of them are showing the geometry, like this, then it is a clear case of mixed model, that is a ARIMA model. So it's a golden rule. If ACF and PACF have the same pattern, then the series is following a ARIMA pattern. Now let's try to detect this thing, that which process the series is following. The dark one is ACF and the light one is PACF. I'm having a significant lag at one time interval, and there is a geometry in PACF. Anybody can guess what it can be? Let's try to understand. We are having a significant lag at ACF 1, and there is a geometry in PACF. Let's go back. ACF, significant positive lag, positive spike at lag 1. So it's a clear-cut case of MA1 process. Got it? See, significant positive lag at spike 1, and there is a damped sine wave or exponential decay. Fine. Next. Now let us see, there are significant two lags, 1 and 2, and there is a geometry in PACF. clear-cut case of MA2. Now, in the previous case, the ACF and PACF were negative, and therefore my YT is equal to phi1 UT minus 1 plus UT. So when we talk about this graph, it's a MA2 process. So YT is equal to phi YT minus 1 minus phi 2 Y2 U2 minus mu 2 minus 3 minus 2. Why it is minus? Because the second leg is the negative. Phi 1 mu 2 t minus 1 minus phi 2 mu 2 t minus 2. Now let us try to understand this one. We are having the geometry in ACF and PACF, one spike is there. Clear cut case of AR1. So YT is equal to phi 1 YT minus 1 plus mu 2 t. ACF and PACF. Significant and first leg, ACF is having a geometry. Therefore, the rate of ACF is much steeper. Here, ACF is constant, you can see, and PACF is geometry. So PACF is only significant in one line. It's a typical case of non-stationary time series. It is a random walk process. Here phi is equal to 1. So YT is equal to YT minus 1 plus mu t. So in the estimation, after identifying that the series is following AR process or MA process, there will be many models which we will create. But we will have to identify the best model on the basis of some criterion. So we'll be using the Akaike information criterion and Squartz Bayesian criterion to identify which is the best model for us. After we have made the model, we have selected the model, there are some diagnostics check which we will have to do. And on that basis, we will try to evaluate the best model. Spatial statistics which we are using is Pierce statistics and Young box statistics, that is a Q statistics. The next step is to estimate those models. Now for each of these models which you have estimated, check. The parameter of the longest leg is significant. If not, then probably you have too many parameters and should decrease the order of P or Q in the model. Check the ACF and the PACF of the errors. If the model has at least enough parameters, then all the errors ACF and PACF will be insignificant. Third thing which you have to see is check the AIC and SBC together with the adjusted R square of the estimated models to detect which model is the parsimonious. Step 6. If changes in the original model are needed, go back to step 4. Now let's try to carry out this analysis in EViews. Now I am having a series GDP. I double click on it, I'll get the series. Then go in view, graph, line and symbol, click OK. And from here, I can get the idea that is series having trend, constant. And I can also see that if I take the difference, probably the series is becoming stationary at first difference, because the series becomes the mean returning series. Let us check by taking the log difference. Okay. Now we'll have to check that is the series stationary or not. View, choreograph. First, we will check at the label. Click OK. Now, needless to say anything, you must be able to understand how to interpret this autocorrelation ACF and PACF. Very clear. Autocorrelation ACF is geometric and PACF is having one leg. Let us go back to our guideline. So our guideline is if PACF is having a single positive spike at leg 1 and other and ACF is geometric, it's a clear-cut indication that possibly it is a AR1 process. Okay. We'll have to confirm this thing by using the probability values. As these p-values are less than 0.05, it is a clear-cut indication that this is a non-stationary time series. Now, I will have to go again to the correlogram. And if I take first difference, is the series getting stationary? Some of the p-values are less than 0.05. But we'll have to check this with the help of unit root test. So let us go back, view, unit root test. We'll first check at level, augmented decay Fuller. Our null hypothesis is GDP has a unit root or the series is non-stationary. P-value is more than 0.05 and therefore it is a clear-cut indication that the series is non-stationary or the GDP has a unit root. Now the same procedure we carry out at first difference and let us try to see. We get the p-value less than 0.05. We reject null hypothesis, which means the series does not have the unit root, which means that the series becomes stationary after taking the first difference. Now, we have just tested that when the series becomes stationary, but we have not generated the series. For this, we will have to generate the series. How we can do this? For this, you will have to write one command, generate, G-E-N-R, generate dGDP equal to D GDP, comma 1. Take the first difference. The first difference series will come into the existence. Let us try to see what happens if I take the first difference. Open as group. So 23, 24, and the difference of it is 24 minus 23, 23 minus 24, and you can see that this is a first difference. Now let us check. Is the series now stationary? Go in dGDP, check the correlogram. Now check it at level only. Because if you will do first difference, it will become 2 times difference. Check it at the level only. Click OK. Here the p-values are less than 0.05, which is not desirable anyway. We'll check according to the unit root test, and this time make sure to keep it level. Click OK. P-value is less than 0.05, which indicates that we are rejecting null hypothesis and the series is stationary. Now we will have to create the model one by one. How we can create the model? Either we can create the model from here, that is I'll enter ls dGDP C AR1 MA1. So it will generate the following results. This is one way in which you can run the regression. Another method, you can go in quick estimate equation. We have already discussed this thing that when you are in this window, it's not necessary for you to write down ls. Now you'll write down dGDP directly. That is a differentiated series. Why I'm using differentiated series? Because the differentiated series is stationary. Another thing is I have differentiated one time and therefore it is a I1 process. So dGDP C AR1 MA1. Enter. A is not defined. Okay. It should be AR. Let me maximize it. Now, whenever we evaluate any model, there are some things, some factors which we consider. One of them is the individual p-values. Are they significant or not? The overall, all these variables, all these terms, are they able to contribute to the dependent variable or not? This is tested with the help of F statistics. Then we see R square. And these are all Akaike information criterion, Schwartz criterion, Hannan-Quenin criterion. They are all related to that which is the best model. Which are the factors which we consider to evaluate the model? The model should have a significant coefficients, that is individual significant coefficients. The volatility should be less, that is a sigma square, which is generated here. Should be lowest, this sigma square should be lowest. the highest adjusted R square, this should be highest, and lowest AAC and SBIC, that is Akaike information criterion and squads criteria. Now this is one model which we have estimated, and we will write down all the details related to this here. ARIMA 111. Now why this terminology is there? Because I have used one term of AR, that is YT minus 1. One, it is difference of 1, that is a series is different one time EGDP, and one MA. You can see here, see I have used this AR1, MA1 and differentiated for one time. I have list down all the parameters which are necessary for identifying the best model. So significant coefficients, there are no significant coefficients, so all of them are 0. You can see here each and every coefficient p value is more than 0.05, and therefore they are not contributing, and therefore it is 0. Okay, next thing which I have listed down is sigma square. Sigma square is 15.26. It's okay, 4.84. I'll change it and make it 4.884. We'll make it 4.84. 14.84. Sorry, 14.8. Now adjusted R square 0.36. It is more or less similar. AIC 5.788. It is more or less near to it. And SBIC 5.94. It's okay. Now we will run another model. Again, we will go back here, and this time I'll change the model. I'll now use, instead of AR1, MA1, I'll simply run AR1 process. Enter. Yes. The results are same as we predicted. To recall, when we had gone for identifying the series according to the correlogram, we knew that this is an AR1 process. See, the p-value of AR1 is less than 0.05, which is a very well indication that it is an AR1 process. So one significant term, sigma square, again we will have to write it down, adjusted R square, AIC criterion, F statistics. The desirable thing in this case, that the individual coefficient should be, the probability value of the individual coefficient should be less than 0.05, as well as in the case of F statistics, the p-value should be less than 0.05. This thing I already discussed in my previous videos of regression analysis of the same series, of the same time series analysis using EViews. Kindly refer this. Okay, again I'll write down all the estimates. So this is now ARIMA 110, sigma square I have written down, adjusted R square I have written down, EIC I have written down, SBIC I have written down. Okay, now I'll again run this series considering MA1 process. Quite surprising, MA is also significant. So now I am having this term is also significant, this is also significant, AIC is also significant, adjusted R square is also 0.31. Okay, I'll list down all of them. Now, how to identify the best term? Normally, the criterion for this is the AIC criterion. Lower the better. Lower the better. So this is, we are not going to use ARIMA 111 because there was no significant term here, and therefore it is very clear that this model we are not going to. So now there is a tie between AR and MA process. So out of this, MA is having the lowest AIC as well as SBIC. Therefore, this model is much better than AR1 process. Okay. Now we will have to carry out some diagnostics on this model. So now we keep this model only, that is LDGDP, C, MA1 process, and we'll have to carry out some diagnostics. So we'll go in view, In residual diagnostics, I'll activate correlogram Q statistics. Legs to include, you can keep it 50. Normally, the thumb rule is one third of the total observations. Click OK. The desirable thing is that now neither of the legs should be significant, or there should not be a spikes in any of the legs. Moreover, the p-value should be more than 0.05. So if we are having spikes at any leg, that leg has to be included. Say for example, if I have got the spike here, then it is necessary that that should be included in the model. Say for example, this is the spike at fourth leg was significant. Then what we will do, I will include that in my model MA4, and then again I will run the correlogram. View residual diagnostics, correlogram Q statistics, legs to include, make it 15. And when I'll include this, see, you can see the spike which was there has been gone. One more. I feel that there is one more spike at 14. Let us include that also. And it will take care of that part also. Again, view, correlogram. Right? So at present, we don't have any significant spikes, and it is not necessary to include MA4 or MA40. Again, you should remember one thing, that if I go on adding the terms here, it will become over parameterized model, and that is also not advisable. You should always have a parsimonious model, that is reasonably two or three terms should be able to explain the variance in the dependent variable. Next, we have to carry out is a lung box Q statistics. So lung box Q statistics is conducted to check the presence of autocorrelation in residuals. I'll go here, legs to include. Let me keep it 20. Okay. And again, you will have to see the spikes. We can see here that the p-values of all the legs is more than 0.05. So we can say that no legs are significant and there is an absence of autocorrelation. Now there is another method to identify the ARIMA models, and that is you can go in add-ins and you can download the add-in. You can activate the ARIMA selection from here and press install. Click OK, close. Now activate again the DGTP file. Again go in add-in, automatic ARIMA selection. You can specify how many maximum ER terms you want, MA terms you want, how many times the differencing you want. I'll keep 1, and I'll keep this 2, and I'll do the testing at 1 and this also and 1. And let us try to find out according to the Akaike information which is the best model. So again it has given me the answer that probably, yeah, here it is. Can you see here? It has given me the answer that the MA process is the best process. This is an automatic ARIMA which you can do. Now after completing, after making the model, now the time is the forecasting, the last stage. So for this, again, I will have to go back in the model. I'll again have to run the model from here, then run it from here. And there is a forecasting tab you will have to activate. Now there is a window from 1961 to 2010. The sample considered here is 1961 to 2010. This is the whole data. Now I will give the command to this that at least predict for last 2 years. So is our model able to fit the observed value correct or not. So 2008 to 2010, I'll change it and I'll specify that make the new series as DGDPF. Keep dynamic forecast. What is dynamic and static forecast? We will see later on. Click OK. Now, if your blue line is between this two red line, then your forecast is good. Now you have to see here RMSE is 3.86 percentage error in your prediction. Again, you can go back here and you can change the range from here and make this as 2008. Okay. Yes. Now generate the graph of DGDP with DGDPF, open as group, view, and graph. Click OK. And you will get this type of graph. Possibly I will have to change some more setting. Make this as 1000. Okay. I can see this thing from here also. I'll select DGDP, open as group, and at the fag end, this is the original series and this is the forecasted series. Original and forecasted. Original and I can also have a graph of it. Graph. Click OK. And I got the graph. Now I can just drag it from here, or rather I'll drag it from this side. Filter appropriate curve. How well the curve is fitting. You can see here the actual and the forecasting. So for more videos on econometrics, kindly subscribe to my channel. You can follow me on LinkedIn and Twitter also.